My name is Jonathan Luton, and today I'm going to be presenting the work of myself and my colleagues on opening up open world tracking. We investigate the question, can we track any object, even those without any training data? But first, why do we want to solve this open world tracking task? The first reason is that this will broaden and simplify how and where tracking can be used. E.g., tracking can be simply extended to track all of the objects that you've seen here, even if there's no training data collected for them. Secondly, for safety. For many safety-critical applications, such as autonomous vehicles, it's impossible to annotate every single object that could possibly be seen. And if some objects that may not be in the annotation set, such as, for example, this pram here, are not successfully tracked, it could lead to disastrous consequences. Note that we're not just talking about rare classes, like the pram that we saw there. We're talking, actually, about classes of objects that potentially can never have be seen before, that potentially are only one of a kind, and thus can only be seen for the first time at test time. As examples, we show some examples of very rare objects that we've taken from the real world. The third reason is to move towards more human-like world understanding. Babies, for example, are able to successfully track objects for the first time they've ever seen such a similar object. Can we create algorithms with similar understanding? Previously, a number of different papers have attempted to create algorithms to track any object. However, no benchmark has existed to measure progress, and thus progress has been slow. In this work, we seek to build this benchmark and hopefully kickstart open world tracking research. We define open world tracking as a task in which algorithms are able to train on one set of classes, which we call knowing classes, and then they're evaluated on a completely disjoint, separate set of classes called unknown classes, which we're not trained on. And the task is to perform well on these unknown classes. We build a benchmark in which we set the COCO classes as the known classes, because these are commonly used for training detectors and trackers. These known classes include people, cars, as well as a number of different animals and common household objects. Every other object is unknown. In our data set, unknown objects include fish, towels, pillows, tanks, monkeys, cameras, and a bunch of others, as you can see here in red. We build our open world tracking dataset, or TOW, tracking any object in an open world, upon the TOW dataset. Here you can see the class distribution of our known and unknown classes for our validation set. However, note that in our dataset, there are further unknown unknowns that are in our test set, for which even the class are unknown. Typically, to evaluate tracking, localization, detection, and association are evaluated. However, in the open world setting, detection needs to be replaced with recall, as we're trying to recall all objects that could possibly exist in this open world setting. As such, we create an open world tracking accuracy metric by adapting the HOTA metric used for tracking to this open world setting. After we have our task, our data set, and our evaluation metric, we analyze a number of baseline approaches, starting with open world detection. Current state-of-the-art proposal-based detection approaches actually perform reasonably well for large objects. However, they're significantly lacking when objects become smaller. In terms of association, we also evaluate a number of off-the-shelf approaches for this open world task, and we combine a number of these approaches into a strong baseline method. Our baseline is able to track a number of object classes that are not seen in any of our trained validation or test splits, truly open world tracking. Our baseline also works on traditional closed world benchmarks, such as Davis and Kitty-Monts. With this paper, we've defined the task of open world tracking, created a data set for it, and a way to evaluate this task. Finally, we've analyzed a number of potential approaches and combined them to produce a strong baseline for others to compare against. We hope that this work we're able to open up the task of open world tracking and see a wave of quick progress with a number of methods, hopefully trying to beat our baseline. So, can you beat our baseline?